The sun at the centre of the solar system is an incredibly hot object. This hot, raging ball of gas.
The atmosphere, it's so much hotter than actually the surface, and we don't know why.
In order to be able to truly see the sun, the interior, the surface, the atmosphere, we have to go into space.
We have had spacecraft that have gone in as far as the planet Mercury.
Mercury is known as the planet of extremes. It is the planet that formed closest to the sun.
The day side of Mercury plus 450 degrees, the night side about minus 180. It's so close to the sun, the dynamics are so much more powerful. Mercury is the easiest place to get to in our solar system, where we can measure the space weather, solar wind coupling with the planetary magnetic field.
We identify a tumbling object.
If it turns out that calculation's wrong, the mission doesn't succeed.
It transpired that a new discovery had been made.
We have found what we believe is ice at Mercury.
We're going to go to the most extreme environment in our entire solar system. We're going to go in and we're going to touch the sun.
3, 2, 1, 0.
This is the story of the exploration of the sun, told by those who dared to do it. The latest step in our quest to uncover the secrets of the sun and the mysteries of Mercury.
That's goodbye, spacecraft.
Humanity, I think, has a general quest for knowledge. We tend to just ask questions and wonder why. The nature is to look up and to look around you and to want to understand your surroundings. And so the first thing anyone looked up and wondered about was the sun.
Studying the sun has always been difficult, mainly because it's so bright. It burns out your eyes, it burns out photographic plates, it burns out everything if you don't do it carefully.
I think it's been, over the years, seen as at sometimes friend and at other times as foe. Described, in literature and in art as being a fiery sort of warlord of the solar system. Giver of life, but then during solar eclipses, older civilizations were fearful that the sun wouldn't come back because they relied on it so much.
The sun is a constant in our lives. It rises every morning, it sets every night. And yet when you look at the sun, you will see that it is anything but constant. It is a continually changing, incredibly active star.
Chinese astronomers were among the first to record the sun's behavior some 2,800 years ago. They noted that dark patches sometimes appeared on its surface and then disappear. But it would take the invention of the telescope for humans to truly begin to unravel the mysteries of our star.
In the summer of 1610, amazingly and somewhat foolishly we would say today, Thomas Harriot looked through a telescope directly at the sun. So he did this in the early morning when there was mist on the horizon, so the sun's light was diminished. But he looked at the sun directly and saw on the surface black spots. The record that he left for us was a drawing of the sun with spots on the surface. But then the most famous observer of sunspots is Galileo, and he made absolutely fantastic, intricate drawings of sunspots, and he monitored them, in particular over the summer of 1612, allowing us to see where the sunspots were. He was able to show that the sun rotated. He was able to show that the sun rotated at different rates depending on the latitude of the sun. And he really showed us that yes, the sun is not this perfect object. It is blemished, but it is interesting and it's changing.
Galileo thought that the sunspots were most likely clouds forming in the sun's atmosphere. Then, 200 years later, an entirely different set of observations began to hint that the Earth and the sun might have some kind of mysterious, invisible connection.
In 1806, a Prussian explorer and geographer called Alexander von Humboldt, he noticed that during a night where there was a strong display of the aurora, his compass needle veered away from its normal bearing. Then, when the auroral display subsided, the compass went back to its previous position. In fact, from May of that year until June 1807, he took compass readings every half an hour, from midnight to morning. And in his work, he discovered a phenomenon that he called a magnetic storm. Today, we call it a geomagnetic storm, a disturbance of the Earth's magnetic field. Humboldt concluded that whatever was behind the aurora, the northern and southern lights, was having a magnetic impact on the Earth.
As investigations into the mysteries of the sun continued, more and more strange phenomena were seen.
In 1859, Richard Carrington, a wealthy brewer in Surrey, in England, his passion was to watch the sun every day and draw what he saw on the surface. And he noticed one day in early September, when he was drawing his sunspots, that he saw these two bright regions form. They sort of flared into brightness. And he was so shocked, he rushed off to find somebody to come and corroborate what he'd seen. You know, amazing new discovery. No one had ever seen that before. He wanted a second opinion. But by the time he got back, the white flaring spots had diminished in brightness and they'd moved. At the same time, in London's Kew Gardens Observatory, an extremely sensitive device called a magnetometer that monitors the Earth's magnetic field registered a sudden anomaly. Then, 17 and a half hours later, the aurorae broke out.
Across the United States and England and various other places, in India where they had telegraph systems, they all stopped working. They generated hundreds of volts of electricity on these lines. There was a person in Washington that was nearly electrocuted. Apparently another telegraph station was burned down in Connecticut. The aurora borealis, which normally hides up in the Arctic regions, could now be seen in Cuba almost directly overhead. In Japan, they were reporting deep crimson red aurora. Miners up in Pikes Peak in Colorado basically broke camp at 1 a.m, thinking that it was daylight. You know, they were fixing breakfast, you know, because it was so light.
So when Richard Carrington saw something on the sun and people directly saw a temporally correlated, you know, at the same time, an event at the Earth, they started to think, yeah, there is something going on here.
Carrington described his observations of solar flares at the Royal Astronomical Society in London that November. It was the first time an event on the sun's surface had been directly linked to events on the Earth. But the cause of this strange connection remained a mystery until the invention of new technologies.
The real revolution for astronomy didn't really happen until the advent of photography, beginning with the daguerreotype method. And that was adapted for telescopic use. And finally, the first photograph of the sun was taken. George Ellery Hale, in the late 1890s, was the first to develop an instrument called the spectroheliograph, where basically he selected a spectral line, I think it was H-alpha, the atomic hydrogen line, and he scanned that line on a photographic plate to build up an image of the sun seen only in the light of that particular transition of that atom. And so all of a sudden, that reduced the brightness of the sun by 1,000,000 times, and now you could just image the sun and see this glowing ring of light.
Using this technique, Hale established that there were strong magnetic fields in sunspots on the sun's surface. Other technology was used to unravel the sun's secrets. It resulted in an even more puzzling discovery.
That hazy atmosphere that you see during a total solar eclipse, the sun's corona, is hotter than the surface of the sun. And that really doesn't make sense. It breaks the laws of physics. You move away from a hot body, it should get colder, but something is happening in this region that really heats this material up to incredible heat.
And we don't know why. If it's that hot, why does the gas stay on the sun? Hot materials move really fast. And if the gas molecules are traveling faster than escape velocity, there should be a wind streaming away from the sun.
And this radical idea was predicted by an American astronomer, Eugene Parker.
In 1958, space was thought to be a hard vacuum. And while the light and heat from the sun could pass through space, the enormous gravity of the sun would prevent any matter, such as gas, from reaching us. But Parker thought differently.
In the 1950s, people thought that space was empty. It's vacuum, it's void. There's nothing in it whatsoever.
The idea was contradicted by several observations.
He went through the mathematics, he went through the physics, and he predicted the hot atmosphere of the sun has a high pressure, so the gas is wanting to push outwards. Meanwhile, the gravitational pull of the sun is trying to hold the gas in. So you have this competition of forces. And if you go up in height in the atmosphere of the sun, you get to a point where the gravitational pull is not able to overcome the outward push of the hot gas. And there's a really important consequence of that. The gas streams out into the solar system. The sun is literally expanding into space.
I realized that we had the supersonic expansion of the outer atmosphere of the sun.
A completely radical idea. Eugene wrote up a scientific paper, submitted it to the Astrophysical Journal, and it got rejected.
Hardly anybody took it seriously. I received several polite and not so polite declinations.
What Eugene Parker realized was that the sun is so hot that the atoms are moving so quickly that some of them can actually escape from the sun. And his calculations suggested the sun should be constantly losing gas, streaming away to make a wind.
It was just too revolutionary to think that the previous view of a sun held together by gravity in its entirety was not actually true.
Parker asked the then editor of the Astrophysical Journal, Subramanian Chandrasekhar, to look at his paper again. Chandrasekhar couldn't find any mathematical flaws in Parker's work.
Chandra studied stars for many years. In fact, he goes on to win a Nobel Prize looking at the lifetimes of stars. He looks at the maths, he looks at the physics.
The editor said to Eugene, so, do you really think there's something in the work you've done? And he said yes, and the editor published it.
But still, it's ridiculed.
Just because the paper was published had no positive effect. They were not behind it because they just believed it was wrong.
3, 2, 1, 0.
Four years after I made the proposal, there was a spacecraft going to Venus.
When Mariner 2 flew by Venus in December 1962, it became the first successful mission to another planet. During the journey, it made another first. It measured the density and composition of a constant stream of particles racing out from the sun. And they did indeed discover that the sun does have this outflow of gas coming from it. The solar wind does exist.
The rest is history.
This discovery was momentous. All of a sudden, space is no longer a void, it's no longer a vacuum. It's filled with material, it's filled with this wind from the sun. The speed of the solar wind, it's almost beyond belief. It's moving between 250 and 750 kilometers per second. And it has some real significant effects on our planet.
The Earth sort of protects itself from the large dynamic forces of solar wind through this fairly stiff magnetic field that it has. In the direction of the sun, the magnetic field gets compressed and strengthened. On the midnight part of the Earth, directly opposite, the magnetic field gets stretched out into a comet-like tail. That tail actually can snap and reconnect itself magnetically. And that causes a flow of particles into the polar regions of the Earth, and that's why we have the aurora.
So the first time I really understood that the sun was having a big impact on our planet was when I first saw the Northern Lights, and I was out in Sweden, in Kiruna, in the freezing cold winter, and I looked up and just saw this incredible curtain of green and red light, and it literally looked like sort of cinema curtains billowing in the wind.
When I actually stood on the ground looking up and watching the aurora, I was like, wow, this is amazing.
And the sudden thought of everything I'm looking at is being driven by what has come from the sun through the solar wind and is impacting with our planet's magnetic field.
Orbiting solar observatories carry a number of complex experiments devised by scientists in NASA.
The orbiting solar observatories were 8 missions in a series. They were launched from the early 1960s towards the end of the 1970s. Collectively, these missions gave a sort of longer-term opportunity to study the activity of the sun. There was an instrument on board that allows you to view the sun using an artificial solar eclipse. So place a disk in front of the sun, block out its dazzling light, and monitor the extended atmosphere around the sun. In 1971, some sort of smudges were noticed in these images. It transpired that a new discovery had been made. Today we call them coronal mass ejections.
Huge amounts of gas, and by huge, up to about 2 million tons of gas, ejected in a filament that moves very rapidly away from the sun. These are like bowling balls of gas being thrown away from the sun towards the planets.
Minus 13, 12, 11, 10.
Skylab made some of the first detailed observations of these coronal mass ejection events.
4, 3, 2, 1, 0.
The Skylab mission was a human spaceflight mission. It was an orbiting laboratory. All the astronauts had been trained in solar physics before they launched, and they were operating solar telescopes that were on board this fantastic space station. One of the real successes of Skylab comes from the number of coronal mass ejections that the mission observed. Long-term observations really showed just how active the sun is, and we can see that these eruptions are basically the mass of a mountain being ejected into the solar system at speeds of millions of miles an hour, maybe even up to 3,000 kilometers a second. They are phenomenally energetic events. Whenever I see the images from Skylab, I'm always in awe because it strikes me just how beautiful the sun is, how much structure the atmosphere has, but also how dynamic the sun is. You know, there are images of eruptions that are absolutely vast. And I always have in mind how dwarfed we are by the sun. The power of the sun and the complexity of the sun and the beautiful structures of the sun are all encapsulated in those images. That allowed us to understand the event of 1859, the so-called Carrington event, because we realised that the sun can reach out to us in a different way.
The discovery answers a huge mystery of all this charged material at Earth. It was coronal mass ejection. And that's what happened in 1859, the Carrington event.
And there have been a number of near Carrington events. In 2012, there was a Carrington-level coronal mass ejection event that just missed the Earth.
As we move to a society that's more and more dependent upon technology, we become more vulnerable to space weather.
With space weather, it's extremely theoretical until your city goes into a blackout for a couple of weeks at a time. That hasn't happened yet, but if we have a Carrington-level superstorm, that event is likely to be very, very real and quite deadly as well.
A Carrington-level event has been predicted now to, cause trillions of dollars worth of damage, could wipe out power grids.
It can cause GPS malfunctions, satellite instrumentation to be damaged, satellites to change their altitude. It can cause high doses of radiation to any astronauts out there. But we never see that big event because they very rarely happen. So the reason I want to study Mercury is because Mercury sees that Carrington-size event every day. It's so close to the sun, the dynamics are so much more powerful. I can study the physics behind the interaction. And if I can understand that physics at Mercury, I can apply that knowledge to the Earth.
Mercury is known as the planet of extremes. It is the planet that formed closest to the sun.
One of the things that we do in planetary science is flyby, and the flyby enables us to do initial reconnaissance to determine if we want to come back. For Mercury, its first flyby, Mariner 10, really was exciting.
Mariner 10 was launched in 1973. The journey there is very complex. We have this issue of not being sucked into the sun, and so actually what we do is lapse of the solar system until our spacecraft and Mercury are in the same orbit. And then we use a little bit of power at the last minute to be captured by Mercury's gravity. And it did 3 flybys of Mercury. We didn't really know what we might find.
And they produced a lot of surprises. They encountered strong magnetic fields.
Surprised us. Mercury has a magnetic field. Wow, who would have thought?
Then they saw the magnetic field look like a magnetic tail, just like they see at Earth.
But because they were flybys and they took images of the surface spanning around 44%, they gave us a snapshot in time, but we got no idea about the global picture of Mercury. And so we couldn't really get a good idea about that until we sent the next mission, the orbiter.
Mariner 10 comes back and says, oh, we're seeing things here that contradict our previous understanding. Then, when resources are available and conditions are favorable, they go back and they do a mission of exploration. And that's what Messenger was.
6, 5, 4, 3, main engine start, 2, 1, and 0, and liftoff of Messenger on NASA's mission to Mercury.
When I became the head of planetary science, Messenger had launched, and it was on its way to Mercury.
Messenger was all about exploring the full surface that we'd never seen before, but also we had to really think about how we develop our technology to survive this environment. It's much more extreme than other planets in our solar system. I think one of the main concerns for us with an orbiter is we go from one side to the other in a very short time period, a few tens of minutes. The day side of Mercury plus 450 degrees, the night side about minus 180. So the extreme in temperature is over 600 degrees swing between one side and the other. So the gradient in temperature is huge. And trying to build an instrument that takes precise scientific measurements is a huge challenge, a huge engineering challenge.
Messenger orbited Mercury every 12 hours. In the 4 years from 2011 to 2015, it took more than 200,000 images of its surface.
What Messenger did was it provided, as its top science priority, a high-resolution image of the entire surface of Mercury. But the mystery was that there were bright spots. There were small, bright spots. And in order for the radar to produce a bright, high-intensity reflection, there were thought to be two possibilities. First possibility is that you have a highly electrically conducting material. The other possibility is that you might have natural geologic formations, but it was very hard to imagine. Nobody's ever seen any kind of geology that would do that. And then one of the Messenger scientists took all of the bright spots in the ground-based radar measurements and laid them down on the map of Mercury. Every single bright spot that was detected from the Earth was inside of a crater that is permanently shadowed.
We have found what we believe is ice, water ice at Mercury, which is really close to the sun. It's in one of the hottest regions in our solar system. So how did the ice get in there? Has it been through meteor strikes, because meteors have water? Has it been through comets hitting the body? Comets have a lot of water. It's really an enigma.
It used to be thought that Earth is the cradle for life, therefore all organic chemistry in the solar system is probably concentrated in the band that the Earth's orbit maps out around the sun. But we're now studying the water cycle, literally throughout the solar system. At one extreme, again, planet of extremes, you have Mercury, where despite the huge temperatures, you actually do have some water trapping. And the rest of the solar system, we're seeing huge reservoirs of water tied up in the ice planets, the moons. So when you're talking about where life is and where the kind of chemistry and ultimately biology that might produce something like us could take place, at the moment it's looking like it might be broader than just one little planet at the Goldilocks distance.
We knew that Messenger was not going to go on forever. We had our nominal mission lifetime of a single year, and our spacecraft survived incredibly well, survived for 4 Earth years. But there had to be a point where the mission came to an end.
Let's end it by impacting the planet. Now, why would we do that? And that's because the European Space Agency has a mission called Bepi-Colombo that's going to Mercury next. And it's going to answer some of the questions that Messenger left behind. And one of the things that we want to know about is when we open the surface up from an impact, from a new impact, what are we going to find? Now, we really have an excellent idea as to where we crashed it, because we did approve doing that. I signed off on it, or it wouldn't have happened. And we crashed it, left a big hole, and so we really are going to be able to tell Bepi Colombo where to look for it. And I think some new science will come out of that. That's the hope. One of the things that Mercury tells us, and Messenger did, is by looking carefully at its orbit and how it's changing, the sun must be losing mass. We know by studying other stars that the sun's evolution will lead it into a phase called red giant, where the surface will balloon out to perhaps further than the orbit of Earth. And when that happens, all life on this planet will be extinguished. Now, when is that? By really looking at the evolution based on our observations of Mercury, we can really fine-tune those answers and determine how the sun is evolving over time. This is really spectacular when you think about it. Understanding our star by looking at individual planets.
The SOHO mission launched in 1995.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition, and liftoff of SOHO and the Atlas vehicle on an international mission of solar physics.
It was a really significant mission because it carried a whole suite of telescopes on board that enabled us to probe the sun inside and out.
It made the closest observations yet of the surface of the sun that really showed how the sun is sculpted by magnetic fields.
One of the big exciting outcomes of the SOHO mission has been the development in our understanding of how coronal mass ejections work. SOHO over the years has literally observed thousands of them because we had this continuous view of the sun. And we understood that they are eruptions of magnetic field that carry mass into the solar system. So SOHO has really enabled us to sort of work more on that Sun-Earth connection through these eruptions that can come our way. The other big discovery that SOHO helped us make was the understanding about the internal mechanisms inside the sun. It sounds really counterintuitive to say that we can look inside the sun, because we know when we look at images, we can see through the atmosphere down to the surface, but we can't directly see inside. So when we say see inside the sun, we're actually referring to a technique in which we use sound waves to see, to probe inside the sun. So the sun is this huge ball of gas, and it has sound waves that bounce around on the inside. And when those sound waves come to the surface, they make the surface breathe. We're able to decipher the sounds, and then from that, we're able to decipher what the conditions are like inside the sun.
One of the most remarkable things about SOHO is it's one of the toughest little spacecraft in NASA's fleet. It's still there today, and the mission has been extended until around 2022. And we should all be thankful, because SOHO is our guardian. It monitors the sun. It's our early warning system of coronal mass ejections and geomagnetic storms.
We have ignition, and we have liftoff of NASA's Genesis spacecraft on a mission to retrieve a piece of the sun.
Genesis launched in 2001. Its aim is to measure the composition of the solar wind, so the composition of the sun and the different layers of the sun. Now, previous missions have done this from a distance, but Genesis is actually going to collect some of the sun that's come to it and bring it back to Earth. Because on Earth, in a laboratory, we can measure compositions extremely accurately. The composition of the sun is really important to understand because the mass of the sun compared to the planets is absolutely huge. And if we know the composition of the sun, we know the composition of the solar system as a whole. The spacecraft is located at a very special point where the sun's gravity balances the Earth's gravity. And there it sat for 850 days, collecting the solar wind, collecting these charged particles from the sun. And then the collectors were closed, and it flies back to Earth to land in a desert in Oregon.
You have a good visual on the target.
Genesis probe is falling through the atmosphere, and it gets to 33 kilometers above the ground, and this is where the drogue parachute is supposed to deploy. And it doesn't. There is nothing to slow the spacecraft down.
And mission manager MTC, be advised, from our vantage point, we do not see a drogue chute, negative drogue.
It looks like we have a no shoot, sir. Vector 200,
Mission
put it on your nose,
manager.
8 miles, look for an impact.
Have a good visual on the impacted vehicle on the surface.
The parachutes fail to deploy. The probe splits into two. And that horrible desert mud enters the spacecraft. The thing is shattered. The disappointment around the scientific community is huge.
The information that we have here from people on the ground is that nothing deployed, and therefore they're treating it as a live spacecraft.
After this dreadful failure, they go to the desert and they pick out little tiny pieces of glass, and were picking out little bits of the collectors. And they actually managed to clean the collectors and perform these really detailed analyses. And actually the mission achieved all of its objectives. It measured the composition of the sun. It measured the composition of the solar wind. It measured the composition of these mass ejections. And it measured the isotopic composition of the sun. And it was incredible. It did everything we wanted it to do, but it just did it in pieces. Studying the sun is incredibly important. We rely on it for light and heat. And we are so dependent on our star for our survival. We really need to understand. The solar probe is the next big challenge. It's the most ambitious mission that we've ever done. Because we're going to go to the most extreme environment in our entire solar system. We're going to go in and we're going to touch the sun. There are still so many things to understand about the sun. There are some huge mysteries.
We already knew the corona is 1 million degrees, but how come?
The solar probe is going to get closer to the sun than any spacecraft ever has. It's going to be within 10 radii. That's within the outer parts of the atmosphere of the sun. It's touching our star.
It really is because we have worked so hard over the 60 years since Gene first wrote his paper to really hone the technology that's needed to do this kind of mission. It really is an incredibly ambitious mission. So I actually did have the pleasure of taking Gene into the clean room at the Johns Hopkins Applied Physics Lab, where we did most of the assembly and a lot of the testing. And it was a really nice moment of taking him in and seeing his reaction to this incredible piece of technology that was going to go and do this mission that he'd really kind of fathered. And so he got very emotional in the clean room, and watching some of the engineering team that were in there that, I introduced him to, and it was like they were meeting, a rock star. And they were very excited to be meeting him. He was very excited to be meeting them. And so it was a lovely moment to just say, this is your spacecraft, and she's going into the solar wind and into the corona, and here are the instruments that are going to make the measurements.
Everybody seems to be in good spirits.
I think everybody loves working on this mission, so look at the happy smiles all round.
And so having that time with him, and again, watching him get just he was mind blown at the technology he was looking at. And the first thing he did was immediately give credit to all of the engineers for their work on that spacecraft. And, he even said to me, really, Nikki, I just wrote a paper. And I said, yeah, it's a pretty good paper though, Gene. And he said, yeah, but, if it turns out that I'm wrong in what I've predicted, I can just write another paper. He said, but if one of your engineers has got any of their calculations wrong, the mission doesn't succeed. And so he said, the pressure on you guys is just intense. And seeing the way you've risen up to every challenge, he said, is just amazing. And I think his favorite phrase is, I take my hat off to the men and women of the Solar Probe team.
Nice to meet you, and good luck with everything.
Thank you so much.
Thanks again.
It's by far the most ambitious solar physics mission we've ever had. And in fact, it has a really fitting name.
I was sitting in my office one day. Phone rang. I picked it up. It was Tom Zurbuchen, and he said, NASA is contemplating putting your name on the solar probe. Did I have any objection? And I was sort of astonished. And I guess I sort of mumbled back, well, yeah, I guess so. I remember sitting there in my office thinking, my God, what have we gotten into now?
The Parker Solar Probe, named after the person who predicted the existence of the solar wind. The first time we've ever named a mission after a living scientist, and absolutely appropriate that it has this name.
That discovery of the solar wind. He was so visionary, he made this amazing discovery. He started a whole new branch of science, the physics of our sun.
I had not been present at a launch, but of course we've all seen on TV. We were invited to a location which had a clear view of the launch, but it was 6 miles away. It's 3 o'clock in the morning.
8, 7, 6, 5, 4, 3, 2, 1. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Wow! Go, baby, go!
The sky lights up, and very slowly this luminous bubble rises up and it goes off, and you realize that it's never coming back.
way to start.
Yeah.
Wow. Here it comes.
That's goodbye, spacecraft. So long, fellas.
Nothing on Parker Solar Probe was easy. Everything was challenging. You're going into this extreme temperature. You've got a lot of solar pressure. You've got a huge amount of heat coming just from the light on the sun because you're so close to it. We used Venus to do our gravity assist. It's a little bit like a handbrake turn. It's counterintuitive because we don't use the planet to increase our speed as a lot of missions do. We actually use it to slow down a little bit. We give energy to Venus. We're very generous. So it slows down and turns the craft in a little more towards the sun. And so that helps us sort of trim our orbits. And we do 24 of them, very close to the sun on one side, out around the planet Venus on the other, and then do that little trim maneuver just to keep making that orbit smaller and smaller, so she will actually get closer and closer to the sun with each one of those orbits. So the idea of designing that mission, getting all those trajectories in place, getting all those maneuvers, knowing exactly when to fire the thruster, that's an incredibly challenging thing to do. She has to be incredibly independent. She has to look after herself because it takes light 8 minutes to travel from the sun to the Earth. We don't have time to joystick the mission. If she's in trouble, she needs to take corrective action. The programming of the corrective action, everything is challenging. Lightweight materials so that you can stand up to these incredible heat. Everything was a big challenge with this mission. Parker Solar Probe today has completed 2 of the flybys through the sun's corona. We're in a very good location where the Earth can see the spacecraft and actually downlink all of our data. So we've just started seeing some of the incredible images and some of the secrets that are being unlocked in these data sets. So we're scientists, we get excited about wiggly line plots. And, you know, we've seen some of the plots and I've actually heard scientists kind of gasp because it's just not quite what you thought, or it doesn't fit any of the simple models. There is so much in there and it's going to take a long time to kind of unravel all of the mysteries that are in these data sets. Right now, we're in a region where we can do co-rotation. So that means, you know, that the spacecraft is sitting above the same part of the sun. And as the spacecraft is moving, the sun is rotating. And we're actually getting some time where we're sitting over the same part of the sun for a long time. And so, you know, we're excited about all the different types of science, the different ways that we can operate the spacecraft and the, you know, again, teasing out the science that is really appropriate for wherever we are in the orbit.
It tends to be visionaries like Parker who are responsible for some of the greatest leap forwards in science. It's people who can really see the simple parts of the problem, the things that really matter.
I think that the whole Parker Solar Probe science team feels a tremendous responsibility to answer these questions. They have been around for decades, but I also think that missions really do inspire the next generation of scientists. You know, if you look at a NASA mission, it is such an incredible, diverse group of people that have a common goal. And so I don't think you necessarily need to aspire to be a rocket scientist or a propulsion engineer. You can be anything you want and really work on a NASA mission.
They make us explore these tremendous concepts that ultimately are going to be our future. They will provide the future science that allows humanity to survive and thrive.